Yeah.
Oh, you got it. Okay. So to reiterate, we're going to create, here's a little sketch, a cloud of particles. We've got gravity acting. We've got a box, and they're going to fall down, settle into a pile. Okay, that's our first little thing. And I'm showing an example of someone who even this simple model is very, very much used by many people who are structural geologists and people who work for oil companies want to understand structural geology because they want to understand where there potentially could be oil trapped. And one of the ways structural geologists learn about these things is that they make sandbox models. This thing is about a meter long, and this literally is sand with colored layers that they start with, and then they push it. And as they push it, you can see the deformation of the sand. And this can be interpreted as similar to, on a tectonic scale, when you push the plates of the earth, they end up, this creates mountains and things like that, right? So there's all sorts of work that where they actually do this. So this is actually, they think of as a model. This is a physical model of a more complicated process, right? And of course, you get the idea. It's like dead easy to do this with PFC. And here's an example where we started with a bunch of particles, we put colors on them, and then we simply took the right-hand wall and slowly pushed it, and we can see how this thing deforms. This is actually a simulation of a real physical device that these people in Thailand in this oil company have in their lab. And their device is essentially a box. It has a fixed wall on this side. It has a bottom layer that's welded to this back wall. And then here's the velocity. And so what they end up pushing this whole thing because it rides along here. There's a gap here. And so that's actually the system that I set up for them. Okay. So we're going to do this. We're going to make this gravity pack and learn about PFC in the process, okay? Then look at this. This should look familiar to one of the people in this course. We're going to look at a granular material, and we're going to take that simple 12 lines of code that let us build a box and have particles settle. And we're going to say, oh, this is an oedometer test. What's an oedometer test? You take material. In this case, these are propant beads. You can see the length scale. And you put them in a rigid cylinder. The walls are very rigid and they don't expand. The idea is that they're not supposed to expand. And then you put a platen on top and you push. And this is, you measure axial stress by taking the force on the platen, dividing by the cross-sectional area. You compute, you measure axial strain. You're applying the strain, right? And so as you push this down, when you load it, you get this stiffening. It basically starts to push itself, pack itself together. It kind of gets to a stable, packed state, has a certain slope. We could think of that. That's a measurement of the stiffness of the system, right? In this case, this is the complicated material. What are we seeing here? What's it doing when we load and unload? Yeah, I'm going to put you on the spot, Ayat. This is your plot.
Oh, it's gonna rearrange and deform basically in the axial direction.
And I'm talking in particular, though, about this. What's this?
Okay, this is when we kept the loading fixed and notice if there is any further deformation. Um, it was like one stage of creep test, but it was too short, like for 15 minutes. So fixed load, um, uh, time dependent, basically.
Yes. So the actual material is complicated, this prop, and it's actually, it's showing a time dependency. It's a really weird thing, right? You load something and you stop pushing and the load is something, and well, you should just you could let it sit there forever and nothing's going to change, right? If I take a pile of sand and I put a big weight on top of it, it's just going to sit there. Nothing's going to change. But for some kind of mysterious reason, there's some kind of microphysics going on with this proppant whereby there's additional damage occurring even under constant load. And how do I know that there's additional damage occurring based on this curve? Can we say anything about the energy in the system?
There is an energy loss. This is where we notice the difference between the loading and unloading, right? So the curve, the area under the curve, basically.
Yes, exactly. If you look at this curve, I'm going up and I get to here. If I draw a vertical line, well, the area under this curve is the energy stored in the system. It's the work done on the material. And if it went down, if there was no time dependency and nothing changed, it would go down the same way. So the energy, the work done loading would be equal to the work recovered when I unloaded. But here, when I go and unload, the work recovered is less than the amount applied. And so that's a loss of energy, right? So somehow that energy is going somewhere. Where's that energy going? What do you think?
And in the lab test, it's going towards fracturing the particles.
Exactly. There has to be energy. There's energy required to somehow drive this damage process that's time dependent. And that's coming from the strain energy in the system. And so that's why you're losing load. This is also a very typical response of a granular material. When you load it, it almost never comes back down the same curve. Usually it doesn't have time to, like if a yacht had not stopped for 25 minutes and she had just immediately unloaded it, the curve would there would still be energy loss, but it would not be as extreme. So they call this hysteresis. You load and unload and you lose energy. And this is very typical of any kind of granular material. And so we're going to take that simple PFC model where we can settle stuff in the box, and we're just going to settle it into this. And then we're going to create a wall on the top. And that's what you see here in PFC3D. Took a bunch of particles, let them settle, and then took this wall and started pushing. And then what was going on is you can monitor the total force acting on the wall. So we're going to give the wall a fixed velocity, which is, in our case, can be interpreted as an axial strain, and the particles are going to push back. And so the wall, you can ask it the question at any time, how much total force are the particles giving to you? So by definition, if we take that force divided by the cross-sectional area of that wall, we can think of that as stress, right? So it's exactly mimicking a physical test, right? So we'll do that. We just need to, what do we do in principle? We just take the system that we had and we add one new thing, a wall, and we give it a velocity. And then we're going to hook up the ability to monitor the stress and the strain as this thing pushes. And then in PFC, there's built-in ability to not only monitor things, but to also plot them like this. And so everything's going to be in PFC. It's not like we're going to run the test in PFC and then dump out all the data to an Excel file and plot it like that. We're going to instead do everything in PFC. So we're going to generate a curve like this, okay? And then we can play with all sorts of things. How do we get the right stiffness, for example, stuff like that. It's also, this is awesome because it's real data of real stuff. So we got axial stress. This is in megapascals. You can see it got up to 35 megapascals, and it took oops, we lost Ayat. Are you back?
Yes, I am. Sorry.
Okay, that's okay. And so we got up to 35 megapascals, and it took 15% strain, which means there's a whole bunch of compaction, if you will, rearrangement. When you let this stuff settle under gravity, it's very fragile. It's not very dense. And when you start squeezing it, you have to squeeze it a lot to start to build up load, right? The loading, you could see how the load built up, the stiffness built up. It got to a normal kind of constant stiffness. The slope is the stiffness. It took like 7% strain before it actually got like fully packed. And the reason for this, a big part of it is because when you start squeezing it, you start creating new contacts. There's little gaps in there. And when you start squeezing it, those gaps come together and now you have more stiffness. And that's part of the reason that this curve goes up. Okay, any questions? That make sense?
Yeah.
Yes?
Yes.
Yep.
Good? Good. Okay. See, this is the problem. If we were in a real room, what I would do is I'd look at someone and I'd say, I'd just look at them and then they would, oh, okay, yes, got it. Okay. Okay. Granular test. Then this is going to be super fun. We're going to say, okay, now let's just take this material that's sitting here before we squeeze it, and let's just add some cement. And in the world of PFC, that means we put in a different contact model that has the idea of bonding. That's our term. I call it cement. We say it's bonded now. And if we bond this stuff, now we have essentially a synthetic rock. Okay. And then we'll go and do the exact same test, but it'll even be more interesting to change this test and to remove the outer wall and squeeze it. And what kind of test is that? What do they call that?
The Brazilian test, you mean?
Nope. Take this material, take this
UCS.
cylinder. Sorry?
UCS.
UCS, unconfined compressive strength test, right? And because you can't do that with a granular material unless it has stickiness. And so that's the simplest. I would say the oedometer test is one of the simplest granular tests, and the unconfined compressive strength test is probably the simplest rock mechanics test, right? So we're going to do that, and we're going to we'll put some really the simplest possible bonding. Then we'll go and make a little more sophisticated bonding. And the reason what we're trying to build here is this. This is a biocemented sand. And you can see the length scale, 1 millimeter. So those are 3 grains of dry quartz sand that have been biocemented. And what this means is what they do is they take this dry sand, they put it into a cylinder under gravity loading, it sits there. Then they take a platen and they place a small load on this. They just put a big weight on there. So now it's all packed, because when you just drop it in there, it's very fluffy on top. So they pack it at some low pressure. Then they inject a fluid that has certain bacteria in it, and they slowly pump the fluid up through this for about, I think, 8 hours. And then that produces a chemical reaction that makes this calcium carbonate form, which ends up acting like a cement. And they call this biocemented sand. And so in this case, one of the things you're interested in is, if you do this process, how much improvement in strength do you get by doing this process, right? And so here's a specimen stress strain curve from UCS test. There are 3 different specimens tested. And this is what the UCS test results look like. And this is what a typical specimen looks like. This is about 50 millimeters in diameter. Looks like at the end of the test. And you can see how it's, in this case, kind of formed a fracture. You can see axial splits that have formed. And you can also, just by looking at this, see this thing is not very well strongly cemented. This is clearly not like a granite or something, right? And you can see the strength. This is in, oh, there's no units here. This is a kilopascal. So this is 3 MPa that we have there. and it's horrible not to have units. Got to have units because it's useless if there's no units. So I missed that. There are units on the plot, but I wanted to make them bigger, so that's why I did these things. There we go, units. And so this is, and notice that the point at which it broke was like 1% strain. The loading here was like 16% strain, right? And notice a bunch of things about this, right? It starts to stiffen when you load it in the same way that this granular material starts to stiffen. And then it's kind of linear. This is actually the Young's modulus, the slope of this curve. And then it reaches a certain point, and then it very abruptly breaks, and therefore the stress drops like crazy. And so this one, when the stress drops like crazy, they call that a brittle failure. But it's never quite that simple, right? Look at the red one. Something happened because it's beginning to not be able to carry as much load. And what the boundary condition here is the strain. They're just moving the platen continuously at a very, very slow rate, probably a millimeter a minute or something like that. And you can see here, this is what we call softening. It doesn't abruptly break. This is probably this is accompanied by as it's forming this localized breakage thing is forming here, and it takes additional strain to keep making it form more and more. And so this example of real data, and the person who did this, Marley Reed, she just finished her PhD at North Carolina State, was looking at the effect of grain size distribution on the response of this material. So she did 5 different samples. The only difference was the grain size distribution, and then looked at the stress strain response. And of course, because we're talking about this, to gain better insight, she also then built some PFC models. And we did everything in 2D, and here we go. Those little green guys are cement. In this case, there's something we call parallel bonds. And there's all kinds of stuff that we were able to investigate here, because this material, as you can see, it's not like perfectly cemented. And there's a number of grains like here where the cement didn't even form. And these little crystals, if you will, that's actually the cement as well. A lot of the calcium carbonate just precipitates on the surfaces, which means it's not really helping in making it stronger. But so she was able to investigate things. Notice that the green here is not at every contact. Right there, there's no cement. Okay, so we were able to look at things like, oh, let's put in cement, but let's only put it in at 50% of the contacts. Let's put it in at 80% of the contacts. How does that relate to the stress strain curves you get? Does that explain them, right? Another thing that could be done with this model is the model itself, because we think of the cement as having a finite size. So that's the diameter of these things. So we could investigate, let's make the diameters bigger. So that means we have more cement. Even though we have the same number of places bonded, some of them have more cement. And so those are the kind of things that she was able to investigate. So that's where we're going in this, okay? We're going to turn that thing into an oedometer test, and we're going to bond it, and we're going to see if we can get this kind of a thing, right? The difference between once we have this test set up is that simply we're going to take this material and we're going to add bonds, and then we're going to do and we're going to remove the sidewalls after we add the bonds. It's kind of fun. If you took this material and removed the sidewalls, it would all just fall out the sides. But if we add bonds and remove the sidewalls, now it's going to have a coherent shape, right? And then everything else is the same. We just push it and we monitor stress strain, right? And the last thing I'm also is because, and this work, by the way, if I haven't mentioned it, this is the work that Ayat is doing for her PhD. And so we set up an example of a very simple model to do an odometer test, and then there's a memo that describes it, and I'll give you that. That might be helpful to get a better, more detailed understanding of this. And then similarly, I helped set this up, and there's a memo that talks about it. And if you look through that and read through that, the memos are kind of an attempt to say, look, this is basic stuff you need to understand about PFC to be an effective user of it. Okay, so you'll end up getting all that. I think we're ready. So here we go. Make a particle cloud. So I'm going to go and fire up PFC. So where are we? PFC course. You can see the screen, right? Yes. Okay. And can you, yeah, and you can probably read it, I think. Tutorials. I'm in the wrong place. Stop. I'm going to call this first one Gravity Pack. So when you work with PFC, you do all your stuff in a directory. Put a project in there, and all the stuff related to that thing is in that directory, right? And then you might do, Gravity Pack 1, and then Gravity Pack 2, and Gravity Pack 3, and maybe you just change a parameter between the two or something. This is how we typically work with PFC. So we've got a directory, Gravity Pack. There's nothing in there basically right now. I have a little text file, which is like a cheat sheet of what I'm going to do. Okay. Not going to worry about that. I'm going to fire up PFC. So flower D. On my desktop, I've installed PFC2D 9.00.181. That's the latest one. And it's set up so that, this is telling it the target. This is a Windows thing, right? It's set up so that when I double click it, it'll execute the PFC executable, which is living in the place where it gets installed, right? And I set it up so that it's smart enough to know that if there's a PFC project file, which is what stores all the information about the model, if it has a .p2prj, in Windows, I told it for that kind of file, I want you to use this program to open it. So once we get going, we're going to have a project here, and we're just going to be able to double click it, and it'll magically start up PFC2D, okay? But we don't have a project, so I have to actually start up PFC2D. So I'm going to double click it. Here we go. This is what it looks like. And I'm aware that most of you are sort of semi-expert users, some of you, but we're doing this for someone who's never done this, like Yoon King, right? Have you actually run PFC ever?
Actually, I have tried that, tried the software before. But,
okay.
Yeah, but I don't really run a real thing with that.
Yeah, sure.
I just
okay.
open the software and click.
Oh, I see. Okay, yeah. So
Yeah.
This is what's going to happen when you start up PFC. You're going to get this screen, and it's going to tell you, because the whole idea is to have a project. So it's asking you, what do you want to do? And so I'm saying new project. I want to create a new project. So, okay. And now, since I'm going to create a project, I have to tell it in what directory to do all of its work and to put that project. So here I need to go and find on my world, here we go, PFC Lectures, Tutorials, directory called Gravity Pack. And so I now need to give a name to the project. And so what I tend to do is do the same thing as the directory. So I'm going to call this Gravity Pack. And I'm going to say .p2prj, because that's going to be my magic convention, so that later on when I click on that, it knows that this is a PFC2D project file. So there we go, Gravity Pack.p2prj, save. And now, if you can see it right there, It just tells me, oh, here we go. This is the Gravity Pack P project. And you are running PFC2D version 9, and there's a subversion number, 181. Every time any kind of bug fix or enhancement is made to PFC, this number goes up by 1. Okay. And you can find that information about when things change by going into the tools, check modifications. And this goes off to the Itasca website, and it tells you PFC or current version 9.0.181. And here it goes. June 16th is when this guy got created, the 181. Here's the new features. Here's the bug fixes, etc. Notice it doesn't say PFC. It says Itasca software. And this is because when we also have other codes. We have a code called FLAC3D, for example, and 3DEC. And all of those codes are in one installation file, MSI. And they also share a large amount of capability. Probably 90% of PFC is exactly the same as 90% of FLAC3D. They share all sorts of things. The user interface looks the same. The logic for doing things. Anyways, so it's Itasca software, and that's why it's going to talk about bug fixes. There was a 3DEC fix. There was a PFC fix, etc. Okay. So getting back to this, whoops, trying to get my program. I'm going to maximize this. That's not the right one. Where's PFC? Right here. And I'm going to maximize the PFC window, right? So here's a command processor. And this is where I type in my commands, okay? So what we have is we have to create what's called a data file. So up here, it says data files, and I'm going to give it the right finger, and I'm going to say new, and I have to give it a name, and I'm going to call it Gravity Pack. Gravity Pack, but this time I'm going to call it P2DAT. We think of this as a data file. This is a data file that's going to be run and executed, and it's going to contain commands. So I'm going to give it the same name, and I use the convention .p2dat because it means it's expected to work with PFC2D. So I'm going to say new, and it says it up here, Gravity Pack. This is the name of the data file. Unfortunately, it doesn't put the .p2dat. And here we go in my directory. There it is, Gravity Pack P2DAT. So this is the PFC data file. So what are we going to do? We're going to say program return. This is going to be the last thing. We're going to give commands. It's going to execute them one by one. When it gets to this, it's going to say return. It's done doing the data file. It's going to do something else. It's going to return back out to here, and we can type commands. So we can either type commands here, but that's not very helpful if you're doing a non-trivial thing. You're going to put your commands in a data file, and then you're going to be able to run that over and over again and make changes. So here, the first thing we're going to do is tell PFC that this is a brand new model. So there's a command, model new. Okay, and then we're going to have to do this. Model large dash strain true. This basically means let these particles move as much as they want. Make contacts form and not form, all that kind of stuff. And then we're going to do this. We don't have to do this, but we're going to give this a title. So we're going to say tight packing of balls into box. And in fact, it's not a tight packing. This is just going to let them fall. So I'm going to say gravity packing of balls into a box. Okay. Now, you should, when you work with PFC, because it's a scripting thing like this, you slowly develop the scripts. You run them and you see if they made sense. And then you change it and you run it again and make sure it makes sense. So at this point, I can actually run this thing and I'm going to be able to see if it actually is using this title. So I'm just going to run it. How do you run it? There's a green arrow here. And what that means, execute the active page. Okay, so what that means is when I click that, it's going to send this line by line to the command processor right here. And it's going to execute those lines. So watch what happens. Click. If I go down here, you can see what it did. It says program call gravity pack. And then here's the commands that it did. Okay, program return. Now it's just sitting out here. So let's look. There's a way of making what we call plots. And so here we go, plots. And I'm going to say make a new plot. And I'm just going to call it my view. That's the plot name. Whoa, here's a plot. This is where we're going to be able to visualize the PFC model. There's going to be a legend on the left, and there's going to be the PFC model on the right. And this is controlled over here by adding plot items. These are things to visualize. So I'm going to say add, well, before I add anything, I have nothing in the model, right? I was going to add balls and look at the balls, but we don't have balls. But we can turn on the title up here. There's a title that's always going to be here, and that should equal the title that I gave it. So let's see. If we hit legend, it's not how you do it. If we hit this checkbox, which the checkbox means options, and in there it says job title, click, and then say okay. Ooh, here we go. Gravity packing of balls into a box. Isn't that nice? That means that this, when I go and I double click now back to this, now I've got the editor window up again. Okay, so when I ran this, right, let's just make sure it really did it. I'll say gravity packing of balls into a box, hello world. Now I'm going to execute this again. So when I execute this again, it's going to do a model new. So all the information is scrubbed out. It's all reset to 0. Okay. So let's see if it actually now is going to have this title with hello world. So I run it and I double click on the plot over here. And there it is. Gravity packing of balls into a box, hello world. One other thing at this point, you can split this window as many times as you want. And I never have done this before, and Ayat can maybe help me. How do I split the window?
It's actually the next one. Yes, here.
Right here? It looks like a split window. Oh, okay. Yes. Split right.
And the shadowed area is where the split gonna be. I use it a lot. It's very useful.
Okay, so here's the data file, and here on the right, I wanted to make a plot of the my view. So here it's this is the plot. So this way, if you want, you can run these things and you can look at the same time. Okay. I'm not going to do that. I'm just always going to look at one thing at a time, and then I'm going to have more screen space. So I think I hit the X over here to get rid of the window. There we go. Okay. So gravity packing balls into a box. Okay, and this is big enough font you can read, correct? Can you guys read this relatively okay?
Yes.
I think you can. I'm looking at my cloned world. Okay, so let's get rid of the hello world for now. We'll come back to hello world when we work with fish. So give it a title. Now, the first thing in PFC is we always need to specify a domain. This, remember, is the world of the XY space in which everything in the model always has to remain. Okay. And so for this system, we're going to make a box, and we're going to make the box be I want to draw on this thing. Temp, here we go. Turn back on my pencil. So of course we have to define a coordinate system, everything else, right? So we're going to make a box. We'll just make it square. And we're going to put the coordinate system, the global coordinate system here. So this is going to be X, and in 2D, there's just a global coordinate system in XY space. And we're going to make this be 2 meters, and we're going to make this be 2 meters. Okay. Notice I'm saying meters. So PFC does not use units. It doesn't care about units. It just assumes that all the properties you give are in a consistent set of units. And so I am going to only use SI units, kilograms, meters, things of that sort. Okay. I will not, I don't like imperial units. I think they're ridiculous. The metric units are far better. And that's what we're going to use. Okay. So we're going to work in SI units. We're going to make this simple box of 2 meters by 2 meters. And so if we think about this, right, we're somehow going to have to define the box, right? We're going to have to tell it, maybe I will have to look at how we do this, where those points are, okay, so that it can build this box. The box will be walls. And this region here, can you see me spinning my pointer?
We can see the painting, but there's nothing going on.
You can't see the
now.
pointer. Okay, that's what I thought.
Yeah.
This region here is where we're going to generate a cloud of particles. We're going to say, make 300 particles in this region. Okay, so we're going to have to put walls there, and we're going to make the particles. Okay, and for this first thing, we're not going to bother to make anything here. We're not going to let them fall. We're just going to create them, let them get packed in there. Okay, so if we go back to the PFC now, if I stop sharing my screen, stop presenting, you should be back to PFC. Are we back? Oh, okay, not yet. And come on. Oh, and now I have to also share this screen. All right, now we're back. So
Yes.
the domain. So this box goes from 0 to 2 to 0 to 2. Let's make the domain bigger. Let's go from -5 to +5 and -5 to +5. So how the hell did I know what to do? So here's what I'm going to do. I'm going to look this up. So there's commands. Every command is documented. So if I select this and I hit F3, it didn't work. If I hit F1, oh, come on. F5, which one is it? Is it model domain? Okay. Did you see what I did? Here we go. The command is actually model domain. So if I put my cursor here and I hit F1, it opens up the manual, and the manual will describe every command. And so here we go, model domain, and now it's expecting a different something else, right? And one of the things it's expecting is called extent. This is the size of the domain. This domain is a box in global XY space. So I'm going to give the X lower and the X upper and the Y lower and the Y upper. And so that's what this is. -5, X lower. So X goes from -5 to +5. Y goes from -5 to +5. Now let's run this and let's see if we can visualize the domain and see if it's making sense. So I'm going to run it. Oh, and look, it's already got a problem. Unused extra parameter 3. So parameter 3, model, domain, that's parameter 3. It's confused. Because if I look back at the command, I'm supposed to say model domain, and now I'm supposed to say extent, and then give it those coordinates. So model domain, extent. Let's try that. I'm going to run it again by hitting this run button. This time it succeeded. At least it didn't give me an error message. Now let's look at the view. So I'm going to click on the plot, my view, and I'm going to add a plot item that's called domain right here. Oh, look at that. At least it's a square. Now let's add a global coordinate system. So that's also a plot item. It's called an axis plot item. This time I got to hit the plus, and here's all these plot items. One of them is miscellaneous. It's called axes. So I select axes here. I say OK. And by default, the axes are going to come up on the bottom left-hand corner of the screen, and they'll always be there. But we want to put them in actual, we want to put them at 0, 0. So notice I've selected over here on the upper right, axes. And now these are attributes of that plot item. So notice it says fixed. I'm going to uncheck it. It's no longer fixed to the bottom left of the screen. Here we go. It's fixed right here. And this is the 0, 0. So we're going to make a box that sits 0, 2, 0, 2 here. So it looks like I might be right. Okay. Let's just see. Let's make this box smaller. It should get a lot closer to this. Just for now, instead of going. So here's what I'm going to do. I'm going to copy this line and I'm going to paste it. And I'm going to put a semicolon here. A semicolon means treat the rest of the line as a comment. And it becomes light gray. So now I'm going to give it a different, let's just go -2 to +2. And in the Y, let's go -3 to +3. And now I'm going to run it. I'm going to look at it. Oh, look at that. It changed. I think it's working. Okay. Any questions? You with me?
Yeah, totally with you.
Yeah.
Okay, totally. Good, good, good. I'm going like super slow. You guys are all smart people. You guys obviously, and many of you have, you could read the frickin' manual and you could run PFC and you could learn how to do this. The whole idea here is to make sure it's all nice and clean and all makes sense. And that's why I'm going slow. Okay. So run it again. You always want to run this all the time. Make sure it's okay. So I made a domain. Now, the other thing we always have to tell PFC is what to do when a new contact forms. And we do that with this contact model assignment table. Contact CMAT something. Let's see if I can get F1. Might not be the right command. So I'm going to look for this command. So I'm going to go in the user interface, Itasca software guide, PFC, commands, PFC, contacts and contact models, commands, CMAT, so CMAT, and I want to make CMAT default. There we go. So here's the description. Contact CMAT default, lots of stuff. That's enough for me at this point to remember. Contact CMAT default. So we have to tell it two things. We have to say what contact model and what properties to assign to its parameters. And so we're going to use the simplest possible one, which we've already talked about, which we call the linear contact model. It has three properties, Kn, Ks, and friction coefficient. So by the default is you're always going to use the model that's called linear, and the properties you're going to give it, property is Kn. Let's just for now, let's say 1e6, 1e6, Ks, 1e6, and friction 0. And in fact, hold on, we're going to make it even simpler. We're going to give no friction. And if we have no friction, we don't need a shear stiffness. But we're just, so the simplest possible model, these are just going to be discs. They're going to have a normal force between them and they're frictionless. Okay, so the entire properties of the whole model are only described by the normal stiffness plus the disc shapes and sizes. Okay. So this is what we're going to do. Let's just see if it runs. So run it. Got past it. That's a good sign. Now look at this cool thing. model state. It says model, where is this thing? Somewhere the CMAT is described, and I'm trying to find it. This is a new thing, and I can't find it here. Where is this thing? Maybe I have to go ahead.
So in the help section, there is contact. If you click on contact, there is some information about it.
Here?
Oh no, I was thinking you wanna see how it works. Yeah.
There's a way in here, it's going to come up later maybe, where it'll actually show me, it'll say the CMAT has these settings. And it might just be because I haven't created any particles and it hasn't used the CMAT yet. So that must be why. We'll see it a little bit later. Okay. Basically, this is what you want to be doing with any numerical model. You want to be, as you're doing it, you want to make sure it's doing what you thought it was doing. So we're going to wait. We can't tell what the CMAT is yet. We're going to assume it really did that. Now, we're going to make some walls to make a box, and then we're going to make a cloud of particles. So there's a command called wall, and it's going to be called wall generate. No, it's not. I guess it is. I think it's wall create. Let's look. F1. Generate walls with specified shapes. That's right. There's also a wall create command. If you do a wall create command, you have to specify all the vertices of the wall. The wall is just made up of facets, which are straight line segments that are connected to each other. The generate command lets you do nice things to make it simpler. Like you can say generate a box. And so now you have to just give it the information about the box. Okay, so that's easier. So that's what we're going to do. So wall generate. And also, before we say box, we're going to give these walls names. And so I'm going to give it a name. I'm going to call it a material vessel. And so this is the command name. And then material vessel is what we call a string. It has to be surrounded by either single quotes or double quotes. A string is a computer science term, and it means a contiguous collection of characters. And we call that a string. And so if we look at here, it's going to talk about this name business, name. And here we go, wall name. If not spelled blah, blah, blah. And notice it says name, and then it's got this little S. And if you click on the S, it means that's a string of alphanumeric characters, blah, blah, blah. And you can even go and learn more about strings. So name, and now I need to say box. And my box is similar, the minimum and maximum X and the minimum and maximum Y. So box. And this box is going to go from 0 to 2, 0 to 2. And so 0 to 2, 0 to 2. And the command processor is very sophisticated. I can do it this way, and I can add all these things to make it more clear, but I could also just do this. I could just do that. They would both work. I like to make it more clear. So every time if it's expecting a vector, which is two numbers, I'm going to put a comma between them and put parentheses there. Okay. So let's see if it works. Boom. Oh, look, it's giving me information down here. The wall, which actually has a name. We'll get to this in a minute. And it says with ID 1 and 1 facet. So let's take a look at the view. Okay, I don't see the wall yet because there's a separate plot item to display the wall. So I go here, and right there I say wall. Ooh, there we go. That looks like it might be right. 0 to 2, 0 to 2, and that's the domain. Let's turn that domain off. Now here I go. Up here, these are the current active plot items. Domain axes wall, and we're seeing it. Domain, here's information about it. Wall, it has 4 facets, information about it. I can click on domain, this guy. I mean, I turned it off. It's not here. It's not displayed. Turn it back on, turn it back off. Okay. So let's just zoom in here now because this is the area of interest, right? Axes, turn them off. Boom, now they're off. Oh, they're too big. Select axes. It has attributes. Size, 0.78. Let's make it 0.4. Boom, it just got smaller. Okay. Oh, let's put it at the lower left-hand side of the screen. Click on fixed. Notice I can zoom this guy all over, but this always remains at the bottom left of the window. Okay, this is often what you want to do. So that's the general idea. You can also go to axes and you can say select here and this little box comes up. Oh, look, I make it big, smart. There's a lot of ways of interactively setting its properties. So now I just did that. If I look the size, it's going to be bigger. Scale. Oh, it actually scaled it somehow. Okay. So keep it fixed, make it small. There. And in the world of PFC, it's not, at 2D, it's not really a big deal to show this because it's always XY sitting down here. But in a 3D model, it's helpful because you'll see a triad of a Cartesian coordinate system, right? Wouldn't it be awesome if Descartes could like come back to life and like see the world now? Okay, so there's our walls. So far, so good. And the wall here, look in the legend, it's made up of 4 facets. And they have actually individually been named. So look at, I say wall, and it says shape. I want to draw it as facets. And here I'm going to say color by. So right now it's coloring by green, facets. But if I say color by a text value, I can say name. Oh, now it's coloring by the name. So blue has the name material vessel left. So this command, when I'm generating a box, by default, it'll take this word and it'll add on left, right, etc. So to make it less awkward, I'm just going to call it MV for material vessel. I'm going to run it again. And now, there you go. Here we go. So the colors correspond to those different facets. I can list it on the console. I can say wall list. And here we go. Wall, here's the name. Material vessel bottom right, top left. Here's the number of facets on each of those, all kinds of other stuff. Every object in PFC has a unique integer ID and it has a unique name. And so automatically by default, because we created 4 walls, 4 facets, no, they're 4 facets of a wall. We each one got a ID. So that's the 1, 2, 3, 4. Okay. We can also just look at some of the facets. Let's turn off the top one on the plot. So I select wall here, color option, and notice here's the 4 things that are being colored and there's a check mark. So if I click off the top, notice the top, watch, look, the top, it appears, disappears. Let's get rid of the bottom. Oh, it appears. Notice it's not shown here. Okay. So this is how there's lots of cool stuff of how we can manipulate these plots. If I want to change the color of the bottom, I double click here on the color and there's a color list. So I turn it black and I have to make sure I tell it to refresh itself sometimes. And now this thing is black. What if I want to make it thicker? So I'm going to go to shape and line size, size 1, 2, 3, 4, 5, 6, right? You can see how it's getting thicker. Okay. So let's keep it kind of thin. Okay. All right. We got walls. Everybody with me?
Yeah.
Yeah.
Good. I swear, at this point with what I talked about, if we just started with this, I bet I could talk to 6th graders and they would understand at this point, right? This is not, PFC is not hard at all. It's a very simple thing. Okay, now let's make a cloud of balls. So I'm going to go and say generate. Just a second. Yeah, this is the simplest way to do it. Ball generate. Now, what's this going to do? Let's take a look. It's going to make a cloud of particles that are not overlapping. So it says generate non-overlapping balls. Okay. The process ceases when the target number of balls are created or when it's not able to make more balls. Think about this. I'm going to tell it, I've given it a fixed space that has a certain size. I'm going to tell it what the size of the balls are and how many to make. So once you do that, there is a finite number of balls that size that fit in that space. Okay, so I could tell, I say make 1,000,000, but if I give it a size that 1,000,000 won't fit, where they're not overlapping, it's going to stop after a while. It's going to say, oh, I made 26. That's as many as I can fit in there. Okay, the very simple way to create particles. They're going to not overlap, but you're not going to be able to give a general size distribution, which is what you typically want to do. But we're doing the simplest thing first. So we're just going to generate, let's say 30 balls in here. So we're going to say ball generate, and we need to give it, so we need to somehow tell it the where to generate. So that's the box command. Ball will fall fully within this box, and they will not overlap the edges of the box, and they will not overlap each other. So again, the box is defined by X min and X max, a Y min and Y max. So we're going to say generate box. Again, it's going to go from 0 to 2, 0 to 2. So that tells it where to generate. Now I need to tell it the sizes of the particles, and it's just going to give a uniform distribution of sizes. And I'm going to specify that in terms of a radius. So let's just see, to screw around with this. It's a 0 to 2 meter box. So let's just try to put a really small number of particles in there. So if we make the radius be 0.2, so the radius is going to go from a minimum radius of 0.2 to a maximum of 0.3. Okay. And then we have to give it the number. So let's say 10. Let's see if this works. Boom. So it says, this time it's a little angry because it's not green, it's orange. Fewer balls were generated than specified, exclamation point. 8 balls out of 10 were generated. And it says in a certain number of tries. What it's going to do is randomly throw them in there. And when it randomly throws them in there, if it overlaps one, it says no good, and it tries to another random number. And if it does it 20,000 times and can't succeed, it says, oh, I just can't do it. So let's look at it. Now I don't see any balls because I have to add the ball plot item. So I go up here, ball. Oh, boom. Is there 8 of them? I can count them. You can agree, right? 8. Over here, ball plot item. 8 balls. They're green. That's what the legends tell me. So let's adjust this. When I work with PFC, because I'm weird, I make them always yellow. I'm going to make so I'm going to go ball plot item, color option. Here we go, ball. Click it, on, off, on, off. Oh, click on the color. Let's go yellow. I actually joke about making them yellow, but over many years of working with PFC, I find yellow to be a very useful color because we're going to almost always plot additional things on top of the balls. And yellow is a good background color that you can put other colors on top. And so that's why I use yellow. I'm also going to make the thickness of this a lot less. So I can go the same thing, shape, ball, shrink factor. Or no, outline. Outline is thickness of 10. I'm going to make it smaller. Thickness of 4. There we go. Okay. Now, so let's run this again, make sure it works. Boom. There we go. Now, before we go any further, we want to save this thing. What does that mean? We can save the project. We can save all the information about the system. We save it to a file on the disk. Then we can shut down PFC, go have some coffee, come back later, and we can start PFC and we can restore. And we will get exactly the same exact state we had before. So let's go file up. Just a second, I clicked something weird. There we go, file. Let me say save project. So save project. The model state is unsaved. I'm just going to say not save the model state. We'll talk about that in a minute. And now I should be able to look and this project file has been updated, 9:21 a.m. That's what time it is now. So now I should be able to quit PFC. File, quit, boom. Now if it really worked, I should be able to double click on this. You know about this Windows thing? I give it the right finger and I say open with, and then I say, I search for it. Let's just make sure you know where that is. So open with, choose another app. Oh, come on, there you go. Select an app to open. So you're gonna always go choose an app on your PC, and the PFC is gonna get installed in program files. And in program files, there'll be an Itasca directory. And in the Itasca directory is going to be Itasca software. This is Itasca software, version 9. Remember, all of the Itasca software gets installed. And in here is the executable, 64-bit executable, exe64. Drill into that. There's all kinds of stuff. One of the things here is PFC2D version 9 _ GUI, graphical user interface version. That's the one you want. So you would say open, and you say always use this when the thing has a .p2prj. And so that's always going to open. This is important to get that set up, because down the road, we're going to do interesting, sophisticated things. For example, we're going to set up 6 UCS tests with the only difference being the strength of the cement. And we're going to be able to tell PFC, fire up a PFC, run a test, shut down. Fire up a new PFC, run a test, shut down. We're going to be able to do all that. To make that work, this needs to be set up so it knows how to open the PFC. Okay. So let's do this again. Gravity pack, double click in this directory where all my stuff is, and it should be like it was before. Boom, it's restored. Here's my data file, but my view doesn't have anything in it. How come? Okay, some of you guys know the answer to this. Why doesn't it have, go ahead.
Because we didn't save the status or the .save.
Yes, exactly. So there's 2 things going on here. There's the overall project, which is storing all kinds of information, like, for example, the user interface stuff. This plot that has walls and axes and balls, that's part of the user interface. That has nothing to do with the model itself. The model is the computational model. And so there's a separate concept of saving the model, and we call this a save file. And so let's run this again. So first, let's just run it and make sure it's there. So now I look at my view, and we're back. But now I'm going to go, and I'm going to say model save. So model save, and I have to give it a name because it's going to save a file on the disk in that location. So I'm going to say gravity pack.p2sav. We like to use these conventions. So this means a save file for PFC2D. Let's just do this, see what happens. Boom, model saved to the file, and it tells you exactly where on the disk it is. Eventually, it's at this point, gravity pack directory, and it created gravity pack.p2 save. Did it? There it is. Made that file. Okay. Now over here, saved states. Oh, gravity pack.p2 save. There it is. Now if I save the project and I say quit, now I'm going to restart it. And it should. So I look at this. Watch this. So here's my data file, because that's the last thing I had open. That's the state of it when I said project save. And now I look at the view. Crap, there's nothing in it. What happened? Shihong, what happened?
Sorry?
What happened? Why isn't there anything in it? I just said I made a save file and I'm not seeing it, and I restored the project. Okay, well,
you need to click click
Yeah.
the SAV, the save
Okay,
file.
so
Save file.
correct. It doesn't, it says over here it has these different saved states, but this one is not the, I have to load one in. So I'm going to go to Gravity Pack Save. I'm going to double click. And when I double click, that's what it does. It restores that. As you're going to see when we run PFC, we might have 6 different save states, like let them fall under gravity and get packed, add bonds, do test. We're going to have all these different states of the model. So we'll be able to click here and choose which one we want to look at. So we have to tell it which one to look at. And notice this, when I double click on this save file, it actually, everything you do in the graphical interface results in PFC commands. So this is what the PFC did. It did a command called model restore of that name. And now it's telling us some stuff. Ooh, this is a save file. This was created by this particular version of PFC on this date. At this point in the model, it's taken no cycles. This is the title. Okay. So that is what we got. So we're at this point now.
I have a question.
Yeah, absolutely. Go ahead.
So, for example, I used to send you some models for you to check. So if I send the save file, you can just restore it and you don't basically need to run, right? And see what I have done.
Exactly.
Oh,
The
yeah.
key thing here is everything is in that one directory called Gravity Pack. So what you need to do is just that entire directory, zip it up and send it to someone. And then once they unpack it, they should have all the same stuff. And then they can double click this and they can go and look at the save files however they want. That's absolutely how you need to do that. Okay? Okay?
Yes, thank you.
Yeah, right? So that way I don't have to rerun the data files. I can just look at the results. But it needs to all stay together and it should all be in the same directory. Okay. Now let's see if you can figure this out. Okay, look at this picture. See where the balls are? Let's run it again. Is that the same? Let's look at those pictures. Let's run it again. Holy crap, that time it only did 5. That's clearly not the same. What's going on here? Why am I not getting the same answer?
The random number.
Random number. What the hell does that mean? Tell us. What do you mean random number? It doesn't mean anything to me.
Yeah, just
you're talking to Yoon King here. She has no idea what you're talking about. Talk to Yoon King. Yoon King, ask him questions. See if you can understand what he says. Go.
Well, I guess I know a little about that because we got the similar thing in lights and CFDM, but okay, just explain it, please.
Okay.
In my opinion, it's just like a different initiation condition with different random number. So if you fix the random number you use to do the simulation, and you fix the initial condition for this. But if you do not fix it, and every time you start to generate balls, you will do it under totally different initial conditions. So it would be really different.
Yes. Let's unpack that. So in this model, PFC is using a randomly generated position when it does this ball generate command. It is choosing a particle out of the size distribution, and then it's randomly selecting a point in that box, and that's where it's putting the ball. So there's some kind of magic here where it's able to randomly do stuff. And so the magic is called an algorithm that we call a random number generator. And the algorithm works by starting with a number, which we call a seed number. It's some integer. And so the algorithm says, you give me an integer, and I'm going to give you a list of numbers that are each one is between 0 and 1. And that list is going to be random set of numbers within 0 to 1. Okay. And that list, so, you know, boom, I set a seed of say 10,000. I generate a list of 1,000,000 numbers between 0 and 1. If I go and give a different seed, I get a different list of 1,000,000 numbers. However, both of them are random, right? Random doesn't mean the same. Random just means random. There's no coherent pattern to them. And so if I give the same seed number, I will get the exact same 1,000,000 numbers. And the generate command is randomly creating a position. And what is it doing? It's calling the random number generator, and it says, give me the next entry in the list. And the entry is always a number between 0 and 1. So it goes and says, oh, my x coordinate goes from 0 to 2, and I'm going to multiply that by 0.5 if that's what it gave me. So as long as I always take the width, I can multiply between 0 and 1, I'm going to get a random x position. And then it calls the number generator again, and it gets a random y position. And so if you can do this, you can give it a command. I'd like to do this right at the top, set model. I think this is the command. Set model, it might be model set. I think it's model set. Let's just see. Model, is it just model random? Who knows? I'm hitting F1. Now I must, oh, there it is, model random. Set the seed for the random number generator. Okay. By default, it's 10,000. So it should be something around 10,000. So let's just go and make it be 10,000. So now, every time I run this, I make a model new. So I scrub everything out. And now I go and I say, set that seed to be at 10,000. So now when I do this, every time I do it, I should get the same answer. So let's look. Run it. There you go. What do we got? 8 of them. Let's run it again. 8 of them. Do they look the same? Run it again. Oh,
Exactly
crap.
same thing.
Sorry. Now let me show you another cool thing as part of this. To see if it's the same, here's what I want to do. I'm going to open a PowerPoint. I'm going to actually make a snapshot of this, and I'm going to compare. And I'm doing this because this is what you always want to do with PFC. I'm going to show you how I strongly suggest you get information into your reports and things like that. Okay. There's many ways to do this. Okay. So first, here's a PowerPoint slide set. So I'm going to say new slide blank. I'm going to make 2 blank slides. Then I'm going to go to PFC. Now, of course, there's many ways to do that. I'm in Windows, right? I could do something like use this snipping tool you probably know about. New, snip this. Now it's in there. I can hit paste. There we go. Okay. You don't want to do it that way. Just think if I want to compare 16 of these things. Every time I use the snip tool, I'm never going to get the same. It's going to be really hard to make that be exactly the same. I want to be able to get exactly the same each time so I can go through the PowerPoints and I can just see precisely the differences. So what I'm going to do instead, this is a view. I can zoom in and zoom out. I'm doing this by rolling the mouse. So let's get this baby centered, use up as much space as we can. Okay, now I'm going to go up here and I'm going to make a bitmap. And so this is going to make a bitmap, a PNG file, a standard thing that we can then look at any way we want, and we can also suck it in to PowerPoint. And it has a certain resolution. Okay, whenever you make a bitmap, it has to decide the resolution, how many pixels. Okay, a very useful resolution that I've learned over many years of doing this stuff, because you want the resolution to be high, but you don't want it to be ridiculously high because then it's a giant file. So I'm using this one, 3800 by 1850. And I'm not sure if that's the default or not. It probably is. And it says window aspect, which means it's going to be exactly, it's going to look like this entire window. and it's a high definition. What happens if I don't do if I don't do high definition, it's lower. It's 1396 by 680. So I'm going to say high definition, and I'm going to go, it's in, by default, it's in that directory. That's where everything is going to live. So by default, it's going to put it there. So my file name, I'll call it snap1. Boom, save. If I look here, there it is, snap1, double click it, and it'll open the Windows photo editor. There's my snap1. This is pretty good resolution, but it's not ridiculously high. This is good for almost everything you're going to need it for to put it into any kind of a report or something like that. So I'm going to open the PowerPoint. I'm going to get rid of this, right? And now, you know, it's very helpful. I got both things open. I got the Explorer. I just drag it, boom. There I have by default. It'll put it in the center and make it that size. So let's make another one and change the render, or let's make another one and see if we got the same thing. Gravity pack, run it again. My view, make the bitmap, snap 2, go to this, go to that, snap 2. Now I can use the magic of PowerPoint. I'm just flipping. They're exactly identical, right? Okay, everybody with me?
Yeah.
This is a very
Yes.
helpful thing to make good high quality snaps. So of course you'd have your Word document and you can then like paste in the PNG file. You should paste it in as a bitmap because you've created a good high quality bitmap. Paste that into anything as a bitmap. And then your Word, for example, is smart enough to scale it up and down and all that, and it'll look really good. Okay, make sense?
I do have a question.
Yeah.
So before we add the model random, when we were generating every time we get different distribution or random distribution of the particles. But when we go to the manual, let's say the default is 10,000. So aren't we supposed to get the same random distribution because we're not using it, so it should be the default. So it should be the same distribution.
Yes, I understand you're completely right, but there's one thing you're assuming, which isn't the case. It turns out that this model random thing does not reset to the default when you do model new. If you read that carefully, it says that if the model random keyword is given after a new command, identical models can be generated. The C does not reset by the new command. So is that what you're talking about, or?
Yes, but yes. So if we, for example, add the model random before model new, it should then stay the default, or how?
So.
Or what does the default mean? Let me put it this way.
Yeah, let's actually do it. Let's go and set this up so that I can make 3 runs, each of which have a different random seed. Okay. Okay, with me?
Yes.
So one way I could do that is do this. Model new, model random 10,000, do these commands. I'm going to copy this. This is not a good way to do it, but I'm illustrating the point. There, it's a single data file. Model random, oh, wait, and I need to say model new. So when I run this, it's going to start over. It's going to set a random seed. Hang, and this is going to be 10,001. Hold on. Let's just make this even better. I'm going to copy the title. Stop. Let's just hang on. I'm going too fast here. Let's get rid of this. Let's set this up here. There. Do a bunch of stuff. There it is. That's what we've been doing. Model random 10,000, save. And I'm going to save it with a new name, Gravity Pack 10,000. So if I run this, that's what we get. And let's actually change the title as well. So I'm going to say gravity packing of balls into a box. And we'll stop after this for a minute. Gravity, random seed 10,000. So let's do it this way. Set the random to 10,000, set the title to that, save it. Okay. So let's run this. And I should, in the title, it says random seed 10,000. You guys with me? And I got a save file called gravity pack 10,000. Because that's what I told it to make, gravity pack 10,000. Okay. Let's go get rid of, I'm going to select that. I'm going to say, give it the right finger. I'm going to say remove from project. I don't want that old one anymore. It's still sitting out here. Delete it. Okay. So now we've got, let's get rid of that junk. There we go. We run this, we get a save file, and it says 10,000. Now let's go, and now I want to go and make the same exact thing, but the only thing I want is to change a random seed. So the simple way to do it is to just copy this. We'll just do it twice. So the second time, notice I'm going to say 10,001 here. And then I better make this be 10,001, and I better make this be 10,001. So it's going to run and make it, and then it's going to start over, and it's going to set the seed to this, and it's going to make a different one. So they should be two different ones. Let's run it. There's two save files. So if I double click on the first save file, that's my view, 10,000. If I double click on the second save file, there's 10,001. I'm just going back and forth. Okay. Everybody with me?
Yes.
Okay.
Yes.
Now, yeah, go ahead. Are you with me?
Oh, yeah. I said
Okay,
yes.
Okay, now here's why it does what it does. Because let's say that doing this process, building the model, actually involved like the whole thing. You got to like build it, you got to let it settle, you got to put the bonding in, and now you have a save file that's ready to go. And that might take 20 minutes of runtime. And well, that doesn't matter how long. But this might take 50 lines of code. It's going to not be a trivial, just a few lines like this, right? And you should never copy code. You should never do what I did. You should never take a whole bunch of code and then copy it and then just change 1 or 2 lines. That's a very dangerous thing, and that's a bad programming practice. So to get around that, I want to do the same thing. Here's what I would do. Let's do it this way. Let's make a new data file called parameter study.p2dat. Parameter study. There's a new data file, nothing in it. I always put program return at the end. So here's what we want to do. We're going to call another data file. No, we're not going to do that. Okay, we're going to do this. Yes. Okay, hang on. Program, bear with me. Program call. I'll call it makeit.p2dat. Okay. Now, let's make another data file called makeit. File, new data file. makeit.p2dat. So again, I'm going to say program return. Okay. Makeit. What's makeit going to do? I go back to this one. I'm going to do this. Okay. This is going to make it, but I'm going to set this random seed at this level. See what I'm trying to do here? I'm trying to set this at the outer level, okay? So at the inner level, the makeit thing, it's still going to do model new, but it's not going to do model random. It assumes that's already been set, okay? And then it's going to run this, and so I'm not going to worry about putting this in here because I would need it. It gets more complicated. I'd need to like store that. And let's just, and the safe, this is a pain. Let's take that out of there at this world. There. This make it thing is supposed to do everything except not save itself. But I'm going to save it out here. And I'm going to do this twice. This is my parameter study. I'm just changing it out here. Okay. Are you with me? The general idea. Set the parameter.
Yes.
Use the parameter, make a save file. And I'm going to manually make, every time I change the parameter, I'm going to change this and I'm going to change the name. Okay. So that means this guy, the program, has to use the random and then it has to do stuff. So that's what it's going to do. Make it. It's going to give a model new. It's going to do everything we want to do. Okay. And this model, when I do the model new, sorry, it does not reset the random number generator. So that means I can give it at this level. So let's just see if this worked. So let's get rid of all the save files that we have. Let's go out here and delete them. And let's see if this worked. Maybe it won't. Run it. Boom. Boom, boom, boom. What did it do? Let's see. It called it once. It saved a file. Gravity pack 10,000. It did it again. Model random. Model new. Blah, blah, blah. Made another save file. Let's see if they're different. And my view, here's the 10,000. That one. Here's the 10,001. It was different. Okay. So does this make sense? This is, do you see what's happening here? Every time I call this, I scrub out the model and I build it. But when I scrub out the model with model new, it does not change the random number value of the seed. That's why I can set it at this level and then do it like that and then do a save. Does everyone get the idea? This is the general idea of doing a parameter study. Okay? Are you with me? People with me?
Yes.
Yeah.
Okay. And what we would do to make this even more general, because again, this is still kind of crude because I'm basically copying code, right? If I had like 10 parameters to do, holy buckets, I would have to sit there and do this, and then I would have to change each one, right? And this is prone to error. What if I don't change these two lines to the same thing? I'm not guaranteed it's going to work. So eventually, we'll go and do this with fish. And so we'll sit there and do something like global parameter, call it something, ran seed equals 10,000. Right? This creates a global variable called random seed. Then I don't need this. And then inside of here, it's basically going to say, it's going to give the command model random, and it's going to use whatever that value is. Okay. And then it's going to do the save. Model save gravity pack dash. Okay. It's that thing plus turn it into a string random seed plus, I'm making up a string on the fly here, plus dot p2 save. And this string, this might not be the right command. Let's just see what happens. Unrecognized word. How do I make this into a string? Who remembers? Oh, this. Let's see if that works. How do I tell it?
I think the random seed maybe.
No, here we go. This entire command is a fish command. Let's try this. Yeah, this looks better.
So the random seed, I think you gave it a different name in the parameter study.
Oh, it's ran seed.
Okay.
Oh, but I didn't run this. Yeah, hang on. That's what, okay. So I need to set the seed, then I need to call this thing. Where is it? Here. Yeah, okay. Let's not worry about this. There's more details here. The problem is this is not going to work. Because the model new destroys the fish variable. There's a way to do this. You can use Python instead. Let's not worry about that. We've gotten off track. But you get the idea. Using fish, you can create a very powerful, like generalized thing, right? So that it knows that number. And then internally, it uses that to do whatever it needs to do. Include, it can change the name of the files, right? So then it'll generate, right? So then you would basically do this to do a parameter study. And all you'd be changing here is this, right? Except what you'd be doing here maybe is, bond strength is something, and you give it different one each time. And then it'll go inside and it knows what the bond strength is, so it can even change the title and say bond strength is something or whatever. We'll show this all later, okay? But I think you get the high level idea, I think. Okay.
Yes.
Let's clean up all this stuff that we don't need anymore. So just get rid of this random seed business. We're going to still trying to do this, but we'll still set a random seed because we want to get this thing to go. Okay, let's see. Let's get rid of those save files. Let's get rid of this parameter. I'm doing remove from project. And I also want to remove them from here. So get rid of the save files, delete. And we're doing gravity pack, so I can get rid of those two. Okay, now we're in a clean state again. Let's run it. What the heck? Okay, hang on. I want to remove them from the project, and then I want to save the project. Okay, now when I run it, there we go. I should just have this. Okay, here we go. Now, what we did is we made a box, and then we made a collection of particles in the same place as the box. But let's go, there's no need to do that, and we want them to fall into the box. So let's make them here, but let's move the box down below here, and then we're going to let them fall. So when we generate the walls for that we're calling the box, let's go from X will still go from 0 to 2, but Y will go from -2 to 0. And let's see that. So then it should be just below. Now I'm going to run this. Okay, now we got that, but we got this top wall here. We don't want that. So we're just going to delete this guy called MV top. And so if I can remember how to do it, I'm going to try it out here, then I'll do it. Wall delete
range.
Just a second, I'll see if this is right. Okay, so I'm going to put this in the data file. Here's what I have to do. So I generate the walls and I delete the top. So I'm going to say wall, so wall delete. If I just give that command, it'll delete all the walls. Return. Run this. Boom, wall delete. It deleted all 4 facets. But I only want to delete some of it, so I want to like filter it. I only want it to apply to some of them. So I use this thing called the range command. So range name set MV top. Now if I run it, what I do wrong here? Help me, Aya. What did I do wrong here? Wall delete range set name. Wall delete range. Oh, range set.
Name.
Set name. Now if I run it, it tells me MV top has been deleted. 1 wall facet has been deleted. So there we go. So now I got this, and I should have the balls, and I'm not seeing them.
Because
I haven't.
Yeah.
Haven't generated them yet. So create the walls. Okay, let's clean this up here a little. Okay. Specify the CMAT, create that box and generate the balls above it. And let's see what happens. There we go. Looks good. Now, let's let those babies fall under gravity loading. So we have to specify gravity. And is it called model gravity? I think it is. F1, model gravity. And I give a number in 3D. I want to do it as a vector. Wait, is that the gravity?
Oh, you do it in
Yes.
2D, so 0 and a number.
Yeah, and we're using SI units. So we're going to say minus 9.81 meters per second squared. Right? Let's see what happens. Looks good. Gravity has been set to that. Okay. So look at this. So let's try to take some steps. Cycle 1,000. Ball 2 has 0 inertial mass. What's going on? Why is it not working?
MST.
Do not set, yeah, density.
I've not set the density. It needs to get the mass of a particle, so it needs to know the volume of a particle, and it's going to multiply that by its density. We specify density in PFC because it's more general, because if you change the radius, you don't have to change the density. It'll automatically figure out the mass. So ball, we call these attributes, density, and let's do 1,000 kilograms per cubic meter. And now let's try to cycle. Okay, let's watch. I don't know what's going to happen. Cycle 100. Oh, they're falling. Let's do a lot of cycles. Million. Oh, why did they not settle? What the hell is going on here?
Because friction is 0.
Friction is
Because
0.
we need a damping.
No damping. No damping. Okay, so they're just going to keep bouncing around. Don't show again. So let's stop this. It's continuing to cycle here. I can see it down there. I also want to always change the legend up here, and I want to say step so that it shows me how many cycles it's taken. That's quite useful. What happened to these other guys? They're sitting out here because they hit the boundary of the domain. And green, stop. By default, the domain, if a particle hits it, it'll just stop and freeze it. It won't move anymore. We could also make it bounce back. We could do a lot of things. We could destroy it. We're not going to worry about that. I mean, something went wrong with our system. We don't want them to hit the domain. So let's put on damping. Well, let's just put it on right now. You can change anything at any point in a discrete element model. So I'm going to say ball attribute damp 0.7, high number. Now continue to cycle. Ooh, there they are. They're eventually going to stop. Okay. Shift escape. I have to hit shift escape to make it stop cycling. Let's run it again now with the damping from the start here. So ball attribute density 1,000. Ball attribute damp 0.7. That's heavy damping. So let's run this. There they are. Cycle 1,000,000. Boom. Oh, that looks much better. Look, they're now moving. So maybe it worked. Let's hit shift escape. Let's change one other thing. So we're going to do this data file, model gravity. Let's just put in pause. So if we run it this way, it gets to that point, and then it pauses, and it goes back out to the console, and it says, I'm paused. And you have to type the word continue to resume processing. So then if I hit continue, it goes on and saves. So after this thing, let's put in cycle 1 million. And so now I'm going to run it, and it's going to pause. I can click on the view, and I can say continue, and now it's going to cycle 1 million. So we can watch what happens, right? Now, how do we know that we're in static equilibrium? What's one thing we could look? What's the actual thing we know? What will be happening if this is in static equilibrium?
Average ratio.
Average ratio, that's one way to automatically try and figure this out. But let's look at the velocities of each particle. And what should happen is, ideally, the velocity of each particle should be exactly 0. But because we only do finite computation mathematics, those sums of forces will never exactly sum up to 0. They'll sum up to what we call double precision on a computer, and that means that sum's going to be down to 0 within 1e to the minus 12 or so. And so let's look at the velocities. We can actually look at a vector plot of the velocities. We're going to draw an arrow at the center of each ball. It's going to be directed in the direction of that ball's velocity. Okay, so first let's just go up here. Let's just run it 100. And then let's make that velocity plot. So continue, cycle 100. There, they're falling. So if it's working, I would expect all the velocities to be vertical. So I should see vertical arrows. So how do I make such a plot? I'm going to go and I'm going to make a new ball plot item. I'm going to turn off the first ball plot item by hitting this guy over here. So now I got a ball plot item. Right here it says shape. And this means, how do you want to visualize? How do you want to visualize the ball? I want to visualize it as a ball, and I'm going to look at certain things. But I want to visualize it as an arrow. So now every ball is getting drawn as an arrow. And by default, it's going to draw the arrow. It's going to be the velocity. So this seems to make sense. Turn the balls on. Now we see them both, right? In the 2D world, the order matters. It first goes through this list, it draws a ball, then it draws a velocity. If I grab this and move it up, now it draws a velocity and then it draws a ball, so you can't see the velocity. So I want to make sure I put that after the ball, okay? So 2, right? If I cycle a little more, I think it'll go faster because they should be accelerating. Now it's 3.14. And this velocity is in meters per second, okay? Because of the acceleration of gravity, right? And there's been nothing acting on here except the body force due to gravity, which is mass times acceleration of gravity, okay? Everybody with me?
Yeah.
Okay, so let's cycle, like, say, 500. Ooh. Now the velocities, look, they're kind of random here. But they're still e to the minus 4. It's not exactly 0, so let's cycle 5,000. Let's just cycle giant, 500,000. Oh, look, e to the minus 14. This is basically, this is as close to 0 as we're ever going to get. This is, you could think of this as thermal noise. It's just, anyway, it's e to the minus 14. Okay, this model cannot change anymore. This model is at equilibrium. Okay. So this would be one way to determine if you're at equilibrium, right? But this would be a pain because we would have to always look at the system to try to figure this out, okay? And we're going to eventually use this fancy solve ratio average command, and it's going to look at a criteria of unbalanced force ratio. But let's first, to illustrate something else, what else could we do here? This is particles under gravity loading in a box. Now, what if we looked at the force on the bottom wall? And if we were to plot the force on the bottom wall versus time, what should that look like? Somebody. Force versus time. Force on the bottom wall. What will that look like?
So it will be 0 at the first time, and then when the ball hit the ground, it will be a little bit larger than the gravity, the total G of the balls, and then equals to the G.
So the force will start out at 0, it will increase, and eventually it'll just equal the same value, right? Yep. And that should be equal to the weight of all the material above. Do we agree?
Yeah, weight.
Okay. Yeah. So the first, what we could do is we could actually monitor the force on that wall, and we could look, when does it not change anymore? Okay. So a crude way to do that is I can say wall list attribute. And these are the different things, attributes of walls. One of them is called force dash contact. That's the total force that acting on the wall based on all the contacts that have forces in them. So I could say, let's go back up to here. Well, let's do it right here first. I can say F3 to recall the last command, wall list attribute force dash contact. And here we go, bottom wall. The force is minus 1.5 E4. This is in newtons. Notice this is the force acting on the bottom wall. So this is in global coordinates. So therefore, the force acting on the bottom wall is negative in the y direction. Make sense?
Yep.
So it's pushing down on this wall. On the right side, it's an X force, and it's positive. It's pushing out. And on the left side, it's a negative. It's pushing out again. Right?
Yeah.
Okay. So we could do this. We could say, let's just do it this way. Wall list attribute force contact, and then do pause again. Let's just do a whole bunch of these things and let's watch what happens. Okay, let's run it. So here we go. And let's show the view. Let's say continue. Force, bottom, minus 1.502. No, minus 1.53. Continue, more cycles. Minus 1.53. It looks like we've already got it. Yes, because the velocities are e to the minus 14. Okay. Let's make this a little more exciting. Hang on. Let's watch it creep up. Shift escape, I think. There. Oh, come on. It's all confused because I was in the pause state and I'm trying to stop it. Just a second. I might just have to start it over. There it is. Shift escape. Okay, go back to this. Let's just do cycle 200. We should see this thing kind of creep up here. So let's see. There's my view. Continue. There. Force on the bottom, 0. Continue. Now they're touching. Okay, here we go. Minus 1.46. 1.46 E4. Sorry, I didn't type continue. Continue. 0. Continue. minus 1.46. Here we go. Continue, should get higher. Minus 1.204. Minus 1.53. I think that's the magic number. 1.53. Okay. So it's at equilibrium, right? Now, we could, instead of looking at it like this, wait, I got to break out of this pause. Come on, interrupt. Just a minute. There, okay. We could actually use what's called the history mechanism in PFC, and we could monitor that value. And then we could plot that value on the screen. In real time, we could watch that plot being made. So let's do that. So here we're going to go. And we're going to say model history. I want to give this history a name. So I'm going to say force on bottom. Call it WP. No, let's give it a bigger name. Force on bottom. This is the name of the history. Model history name, force on bottom. I got to remember the syntax. Come on. Model. Oh, this is actually, okay. This is a history related to balls. This is not a history. This is a history related to walls. Let's see if there's a wall history command. Let's go to PFC objects, walls, commands, wall history. Wall history, I can give it a name, and I can monitor all these different things. So I want to say force contact in the Y component of the force. Because think, the wall has a total force in the x-axis and a total force in the y. And since you're only monitoring one value, you have to choose, because the history is just sampling this value constantly. Every 20 steps by default, it's going to sample this. So let's go. The name is force on bottom, and what we want to do is force-contact -y, and let's put in a return. Let's run it and see if this worked. It says no object for history specified, because I didn't tell it which wall. Okay. And how do I tell it? I tell it by saying name. So I'm going to say name, and then I give the name as a string. So which wall? The wall that's called MV bottom. See if that worked. There. It created a history that's called force on bottom, and it is the total Y contact force acting on wall 1. And which one is wall 1? If I say wall list, I see that wall 1 is MV bottom. So we've hooked in our history. And I want to sample this every step. And I think this is the command. See if this works. Yes. So every single time step, it's going to sample that value. Okay. And now, so let's just run this here. Let's get rid of all these pauses. Let's just do cycle a million, you know, I don't know. 50,000. Get rid of all this other stuff. Just run this with that history in there. Here's my view. Velocities are e to the minus 14. Now, let's make a plot. Hang on, I don't want to do it 50,000. Let's just do it 3,000. Seems to be enough. Here we go, e to the minus 14. Now, let's see if we can make this plot. So this is another plot item. It's called the history plot item. So I go up to here, to the plot item list, and down here it says charts, history chart. So I double click. Now this plot item is being shown. Let's turn off all the other plot items. Here we go. It's going to plot something versus step number. but I haven't told it. Here it says history, but I haven't told it to take of what. So I select the history plot item, and here's an attribute. And it says right here, these are all the existing histories in the model. And one of them is this thing, force on bottom. So I say plus. Oh, look at that. So it's plotting in this color that history that I called force on bottom. And you can see it was really high, and then it, and now it's not changing. Okay. And of course, and let's go and do this again. Let's now look at this a little closer. Let's just run this like 500. And let's do pause. So boom. Look at the history. Now continue. There it is. Now we want to see the balls too. Well, let's just draw those guys on top. Let's draw the walls on top. There we go. Let's make that history red because I'll see it better. So I say series, force on bottom. Here's a color, red. Okay. And it looks like it's almost in equilibrium, right? Cycle another 200, 300. It was still bouncing around a little. And now it looks like, there we go. Nothing's changing here. Okay. Is everybody with me?
Yeah.
And it's plotting it versus step number. So right now it's step number, oh, it's going to go for a long time. Hang on. This should be the total step numbers because we started from 0, 5,800, right? And we can do all this cool stuff. We can give labels to this, right? So we can go to axis 2, which is the y-axis, and we give it a label here. Force on bottom wall. Make sure you give it units. There we go. That's force on the bottom wall versus step number. Oh, and let's make the step number start at 0 because it really started at 1 because I started sampling at 1. So let's go to axis 1 and say minimum. Here it says automatic. The minimum was 1. The maximum was 5,800. Let's change it to 0. There, now this is a cleaner plot. Okay. So there we go. And we can monitor anything going on in the model. Displacement of a ball, force on the ball, force of the contact, you just name it. Okay. We can take multiple histories at the same time. And then we can plot them all on top of each other if we make the same x-axis. Okay. So PFC is very powerful in that you can do everything inside of PFC. You don't have to keep screwing around and dumping stuff out to Excel and making plots and stuff like that. Maybe for your final plots, you might want to do that. And these histories exist in the model. I say history list, and here right now, there's only one of them. But you can, there's a command, I think it's called history dump, and you can dump this data to a file, and it dumps it into a text file, and you can suck that into Excel. Okay. Making sense? You guys with me?
Yeah.
Okay. Now the other thing, yeah, let's do this now. Yeah, let's just a second. I'm trying to figure out what we want to do. Yeah, let's do this now. Okay. Let's make sure that the weight of all the balls is equal to this value. Correct? Does that make sense? That's what it should be.
Yeah.
Okay. To get the weight of the balls, let's screw around here and make it a simpler system. Let's make these go. We're going to generate 10 balls that all have the same radius of 0.2. Okay, so let's run that. And now let's continue. There they go, right? Looks like we're at equilibrium. Notice a bunch of stuff. They all have the same radius. Look at how they packed. They packed in this crystalline form because that's what we would do. Frictionless things, all the same radius. If they have a distribution of radiuses, they pack in a arbitrary way. Okay. Just to show that, right? And let's make more than, well, they're so big. Let's make them a little bit smaller. 0.1 to 0.3, 100 of them. And let's do 5,000. Let's run this. Now it gets a little more exciting. So from that size distribution, they're still readjusting by these bumps, but now it seems to be the same, right?
Yeah.
Here's what I wanted to do though. Let's make them all the same radius, and then we can calculate by hand what the weight should be. And we can compare that to this force on the bottom wall. You with me?
Yeah.
Okay. So let's make all the radiuses. We got 100 guys with radius of 1. Let's make sure we can actually, at that size, we get 100 of them. 62 balls were generated because at that size, they don't fit in that region. Let's make it a little smaller. 0.05, make them all the same. Let's run this. Okay, 100 balls got generated. There they are. So 100 of them at that. And let's just cycle a lot and make sure that they fall in everything. Oh, okay. What's going on? Ball 10 has 0 inertial mass. Oh, it's because I had a return here. And let's get rid of the pause and cycle 5,000. Here we go. Falling, readjusting, rattling around. There. Seem to have reached the point. Okay. Let's first make sure this force is the same. This is supposed to be the force on the wall. So if let's list it. Wall list attribute force. No, just wall list. No. Wall list attribute force contact. So it says minus 7.7 E3. 0.7 E4. Yeah, so that's minus 7 E3, right? It should be this number because that's what we're monitoring. And it's not changing anymore. Okay. Now, let's work out what is going to be the mass of this thing, the weight of this thing. This is the last thing we're going to do. Okay, somebody remember, because I'm going to switch now to this guy. Share screen. Start broadcast. Come on. It should be switching now. Okay, come on. Share video, share screen. Oh, I do have the screen shared. Sorry. There, you can see this. Okay, let's work this out. Let's see what that weight's supposed to be. And you guys are going to help me. So we've got
Oh, sorry. Could you guys see the share screen? Because I can't see that.
Oh.
Yes,
I
can. I see it.
Oh, yeah. Now I can see it. Thank you.
It says R equals. Okay. So R equaled, I'm going to cheat here because I can see this, 0.05. So 0.05 meters. The number of them is 100. Okay. So, and we know that the density is 1,000 kilograms. We got to get these units right. Kilograms per cubic meter. Let's see, density. Yeah, that's right. So we should now have everything we need to calculate the total weight of this system, right? So you guys help me here. The weight of a single particle is the density of that particle times the volume of that particle, right?
Yes.
And what's the volume of the particle?
3/4 pi r cube.
Okay, so if it was 3D, it would be 4/3 pi r cubed.
Oh, yeah.
Okay, do we agree if it's 3D? But this is a 2D model. So in 2D, what do we got here? What do you think this is? We've got radius R.
Why? So,
And we've got
Yeah.
thickness 1.
so it's the area, actually.
Exactly. So it's pi r squared times thickness. But thickness equals 1 meter. So volume of a particle equals pi r squared times 1. That's the volume of particle. And so let's work it out. And then so if we take now the total weight on the bottom is going to be equal to 100. There's 100 of these, right? So it's going to be 100 times whatever a weight of a particle is. Do we agree?
Yes.
Yeah.
Okay. So let's just write this out and then see if somebody has a calculator. So the weight of the particle is density of the particle, 1,000 kilograms per cubic meter, times the volume of the particle by what's radius 0.05 meters squared times thickness 1 meter. And that's everything. So this becomes cubic meters. It crosses with that. Oh, so now we have kilograms, but we got to multiply this by, this is the mass. The mass is density times volume. So we got to multiply by acceleration of gravity. Does that make sense? So we got to
Yes.
multiply this by 9.8 meters per second squared. And then the units, the meters cancel, and we're going to get kilogram meters per second squared, which is a magic Newton. Okay. So somebody
7,000.
give me the number in scientific precision to like 3 digits.
Okay, it's 7,704.7559.
No, give me it like A.7.234 E6 or something.
Okay, it's 7.7 E3.
Okay, just a second. 7. Give me some more significant digits.
7,047.
7 point, read it, tell me, 7 point what?
7.70475.
Okay, that's enough. E to the what?
3.
Newtons. Okay, this should be what we're getting. So is that what we're getting? I get, it's on here, 7.705 E3. Oh, we got it. 7.705 if we just look at 3 figures. Are we good? Does everyone agree?
Yeah.
Okay, this is cool, right? So you see, looks like PFC is doing what we thought. Remember, it's disks. That's the little trick here. Now let's play a little game. We just have a minute here. I'm going to do something. We're going to see what happens. In order to show this effect, I need more particles in the system. So let's make some more particles because they're going to fit. See if we can make 1,000 if it'll fit in there. It did. Cool. There. And we're at equilibrium. And now it should be 10 times bigger, right? Because we made 10 times more particles. So there should be, it should be e to the 4. Wall list attribute force contact 1.89. Well, let's not worry about this. Okay, it should be not where, but maybe it's not a D. It should be. Wait, why is it not doing this? Hold on. We did 1,000. Are we at equilibrium? Now, what's the weight now? Still readjusting. Still readjusting. It's going to take a lot longer here. Still readjusting. Now it seems like it's not. There's my velocities. They're e to the minus 13. This shouldn't be changing anymore. And I'm getting here 2 force on bottom. Okay, what's wrong here? I don't know what's wrong here. Why is this not 10 times? What am I missing? Why is this not 10 times? Oh, you're still seeing, you're not seeing the screen, are you? You're seeing the
Yeah.
stupid. Okay, hold
Yeah,
on.
but we are imagine it, so it's fine.
Let's look at this. Hang on. The weight of a, if all I did was make more particles, keeping them all the same size, do we agree? This number becomes 1,000, which means
Yeah.
the weight should be 7.705 times 10 to the 4 newtons. If we make 1,000 instead of 100. Does that make sense?
Yes,
You guys,
it makes
does that
sense.
make sense? Okay,
Yeah.
then let me
Yeah.
stop sharing this screen. Okay, let's see. This is interesting. Trying to stop share my screen and then we'll be done here. Stop presenting and now share this screen. Okay, go back to here. Gravity pack. Look at this. I'm generating the same radius, but 1,000 of them. Let's return. Let's make sure I got 1,000. Oh, here we go. Fewer balls were generated. 1,000 of them don't fit. Okay, hang on. This is why it didn't work. Oh, we only get that many. So how many fit? 246. Well, let's just do that then. Let's do 220. Yeah, there. They all got generated. Run this. Now someone do the calculation for the weight. Here, I can do it. It's what was that previous number? Okay,
The previous number is 7.7 e to the 3. Now it is 1.6 e to the 4.
Okay, so you're saying you did that calculation 1.6 e to the 4.
Yes.
I'm liking it. Here's 1.6 e to the 4. If I just a crude look, right? And if I print it, there we go, 1.69 e to the 4.
5.
Okay. Now, good. Now let's change one thing. Let's change the friction coefficient so that there is a friction on here. So let's make the friction coefficient, let's say 0.5. And now we have to give a shear stiffness. Let's make it the same, 1E6. Okay. Now let's run it again. Now it's not packing in a perfect way anymore. It's more of an arbitrary packing. And it looks like the force is no longer changing. Still going a little bit. What's the number? Okay, what was it supposed to be? Ayat?
1.695.
1.69. It's only 1.53. What's going on? Let's cycle some more. Maybe it's still changing. Looks like this is staying the same. Let's do Shift Escape. Let's print it again. Okay, there we go. That's the best we're going to get. It's not as much. It's less than the weight. Where is that extra force going?
Because of the friction from the walls.
Boom. Yes. Notice right and left, they have force pushing up. It's negative. So they're pushing down. So the wall on the left has also force pushing down, which means it's carrying some of the load. If we sum up all of this, it's going to equal the actual weight. Okay. How can we see that? Let's look at the force chains. Remember the force chain business? How are we going to do that? So we're going to say the contact plot item, and we're going to go there and say text value force chain. We're going to say scale by force and directed, and I'm going to change the color to black for compression. redo the plot. Here we go. Force chains. Okay. Notice they're bigger on the bottom because of the weight above. That makes sense. But look on the sides here. This force is pushing that particle upwards. So is this. So that's where the load's getting shed into the wall. Let's run it again with zero friction, and we're going to see that these force chains should all be perpendicular. Zero. Doesn't matter what KS is. As long as friction is zero, should do this. Now the forces are building up. Look at those babies. There's no friction, so there's no force carry. Right? It makes sense. The wall is taking some load. As that stuff pushes down, there's friction. So some of that force is pushing into that wall. So look at the history. Pretty close. Looks like it's not changing. Let's confirm this. F3. And there you go, 1.7, e to the 4. And the forces in the right and left in the y are 0. Okay. Notice also the x forces are equal and opposite. It's pushing on the right and it's pushing on the left at the same amount. Okay.
Okay.
You guys with me?
Yeah.
This is a
Yeah.
real
Yeah.
thing that happens. Like if you have a big silo with grain in it, right? You've seen those things probably. Like they put grain, and these things are huge. These silos are like, some of them are like 100 meters high and probably 10 meters across, and they fill that with corn, right? When they build those silos, they have to account for the fact that quite a bit of force is actually going into those silo walls. So they end up reinforcing those walls so that they don't buckle. I found out about this. We're going to end on this story. I found out about this when I was doing work with people from Dow Chemical, DOW. Dow Chemical is an international American company that makes chemical products. They have about 150,000 employees worldwide. And there's a group at Dow Chemical that are experts at granular flow. And you would say, why does Dow Chemical care about granular flow? Because I always thought that chemicals, I think of liquid. I think of nasty corrosive liquid in big tanker trucks as being chemicals. But most chemicals, when originally produced, are in the form of pellets. Okay, they're pellets like pills, like the size of corn kernels. And then it's shipped as pellets. And then when the person wants to use the chemical, they typically add water. Okay, so if it's shipped as pellets, that means think of a typical shipping process as taking all these pellets and putting them in a train car, in a train box car. And you've probably seen these train box cars. They have openings, square openings on the bottom because they're bins. And so you fill them with the pellets, and then eventually when you get to your destination, you open the bottom and it flows out of the bin. And sometimes when they make new chemical formulations, there may be some stickiness that occurs between the pellets, and they want to make sure that it's not going to get stuck in the car so that it'll still come out when they do this. And when they make new things, completely new things, they can't make a lot. They make a small amount, and then they give it to this group of experts in granular flow, and they say, you tell us if it's going to be a problem. So these guys are not able to get enough to actually load up a train car and observe. So they have to work with a small amount, which means they have to do small scale tests. And for granular material, it's very sensitive to size. And you can't directly always translate a small scale test into that. So the result of all this is they use PFC to try to answer some of those questions about the granular flow. And so I was working with those guys some years back, and they told me this story. They told me this business about if you actually study granular flow, the first thing you learn is that a large amount of load gets carried in the walls of these bins. And here's the story that they told me It's a great story, and I don't know if it's true, but it's a great story. So I was like, wow, that's really interesting. And they said, yeah, let me tell you a story you'll never forget about why that is. So I said, okay, this is great. I love stories. So they said, years ago in the early 1900s, this was something that the physicists figured out. Okay. And I don't remember who it was, but there's a well-known, I think he might have been German, I guess mechanics guy, but I guess they didn't call them that. They probably called them physics guys. And he figured out it had this theory about granular materials and how the load will arch into the walls. And so back then, if you were a German professor, you know, you were very formal and you would give very formal lectures. You would go on a stage, you would be dressed up in a suit, and you would slowly give people, you would lecture, right? You certainly wouldn't do an experiment on the stage. You would lecture. However, this guy came up with an experiment. And so here's the experiment. He pushes out onto the stage a big steel tube that's probably, I think, about 50 millimeter diameter, and it's vertical. And it's hooked onto a frame, and it's probably about 2.5 meters high. And it's about a half meter above the ground, and it's on a frame. So can you picture this thing? A 3-meter high tube, and a tube's only, I think it was only 25 millimeter diameter, pretty small, okay? He has this tube. At the top of the tube is a plunger, a piston that perfectly fits in the tube, okay? With me? Piston.
Yeah.
Yeah.
Okay. Now, here's what he does. He goes and he takes, of course, he's a professor in those days. And so he smokes a pipe and he smokes cigarettes because that was the thing that sophisticated people did in Germany. So he takes out, and of course he was sophisticated, so he didn't buy his cigarettes. He made them himself. He rolled the tobacco. So he has tobacco paper, they call it, in his pocket. Tobacco paper is very thin. It's like a coffee filter. And you put the tobacco in and you roll it into a cylinder. So he takes out a piece of tobacco paper, which everybody knows it's a common thing. And he takes it and he goes to the bottom of the cylinder and he puts it, he wraps it, he sticks it on there, and then he gets like a rubber binder and he puts it around it so that now you have this paper at the bottom. Okay?
Yeah.
Got it? You visualizing this? You get the idea so far?
Yes.
Okay.
Yeah.
Now,
Yeah.
he then goes and he says, now my assistant will demonstrate. Okay, because listen what the assistant does. Okay, so another guy comes out and the guy gets on a chair so he can reach to the very top of the cylinder, and he has some sand. And he slowly, carefully pours the sand into the cylinder. Okay. And he fills it up to near the top. And then he goes and you can see, and the professor says, look, we can see the weight of that sand is not breaking the tobacco paper. Okay.
Oh.
Okay. Then
Yeah.
he says, now observe, if you do not believe me, this is a very powerful effect. There's a large amount of load because it's a very rough cylinder. Okay. There's a lot of load. In fact, the majority of the load is carried in the walls of the cylinder because it's very long relative to the diameter. Okay. And so he says, now, remember the thing I said about the piston. Okay. So now this assistant climbs up again on the chair, puts on the piston. Now the piston has a horizontal bar about a half meter long connected to it. And it's a bar so that he can reach up and he can grab the bar with both hands as if he was doing a pull-up. Okay. So he goes now and he puts on the piston, puts on the bar, and then he pulls himself up so his legs are no longer on the chair and he's hanging there. The professor then pulls away the chair, and so you can imagine this guy hanging there, Okay. And then the professor says, observe. And he reaches down with his hand and he simply pulls away the paper. And of course, the whole entire thing immediately falls. The guy falls to the ground and the sand all drains out in a half a second. So I don't know if that story is true, but it's a hell of a good story. And it illustrates this idea of how the load in a granular system is being transferred into the walls. Okay. So that's why a granular material is not like a fluid. If that was water that was in there, nothing is transferred to the walls. So the entire weight, so the pressure, this has to do with pressure. When you first start looking at granular material, I had assumed that the pressure on the bottom was just a uniform increase with depth, just like water. And of course, and because of these effects, it's not. Okay. So thank you for your attention. Okay, we're going to end lecture 4 today. We're going to continue on the path of working with PFC, and we're going to slowly get more complicated as we move along here and do the things I outlined. Okay, we're almost done with this. What we're going to do now is say, wait, we can use the solve average command, and we'll just do it and give one command, and everything will. In fact, wait, this will just take a second. So instead of doing cycle, we're going to say model solve ratio average 1e minus 5. Let's put a pause there. Now let's run this. Look at it. Okay. Oops. What did it not like? Oh, I spelled pause wrong. Give me a second here. Pause. Let's see what happens now. See if this automatically can work. So here's my balls, my walls. Continue. Here we go. Falling. There's my force. Ratio average is pointing out down here. It's now 3e to the minus 2. You can see it's not at equilibrium. You can see how the force chains are changing. It's not in equilibrium until those force chains don't change anymore. It's still bumping around a little. It's still slight. There we go. One, done. So it took 7,000 cycles to reach equilibrium. And so that's what you're going to use typically when you're doing real problems, is you're going to always be using this ratio average. And depending upon, so we used 1e minus 5. So if I look at the velocities, notice, look at this. There is a coherent velocity field. This is not at 100% full static equilibrium. It's e to the minus 5. Notice this hunk of material is still flowing and pushing this guy up.
Yeah.
Right?
Yeah.
And if I got to go a little farther, solve, but if we actually at this point were to look at the force chains and were to cycle some more, the force chains are probably not changing anymore. But this is still going on at this much lower level. So let's see what happens if I run this further. Model solve ratio dash average. Now instead of 1e minus 5, let's do 1e minus 7. And it's going to go further. Oh, look, now it's done. The ratio average was that, but it's still not e to the minus 12. You can still see there's a small amount. These are very small, right? This is meter. This is 1/10,000th of a millimeter per second. But it's not there. So e to the minus 7 is still not perfect. E to the minus 9. Cycle some more. Oh, look, almost. Now we're e to the minus 9. And now we're starting to get, they're still kind of rearranged. Oh, there we go. We're going to eventually reach e to the minus 12 velocity. And it's just going to be, you could think of it as thermal noise, right? Now there's no more coherent motion. Every single particle is just rattling around at near zero, as close as it's ever going to get. Okay. So when you see these coherent motions, that's indicating, again, when we run it this way, and we go to the 1e to 7,000 steps, and we'll look at the velocities. Super cool. You're going to watch it rearrange. It's kind of, you can see it vibrating, that those velocity vectors are zipping back and forth. And as it starts to get to more equilibrium, it gets, now it's this sort of coherent pattern of moving around. Again, if we look at the force chains, which is really what we care about, now we can continue for a long time. Look, the force chains are not changing anymore. This is like very low level vibration, sort of coherent motion going on. If we're going to now do an oedometer test for most things that we're going to do on this material, we're going to get the same answer whether we go further here to static equilibrium or whether we stop from before. It's usually the force chains. If they're not rearranging, that's pretty much sufficient to now we could go and start loading this and look at what it's doing and stuff. Okay. Does that make sense?
Yeah. Yes.
Okay. So this is the idea of static equilibrium. This is fundamentally important in all of these runs. And so we've got damping on here. We've got high damping, which is making it eventually stop bouncing around. And then they've got this vibration happening of the particles, and that's slowly getting removed. We're getting a stable assembly. The force chains are showing us that it's essentially stable in carrying its forces and stuff. And so we're going to be using that solve ratio average. And 1e to the -5 is probably about enough for the vast majority of systems. Okay, because if we changed, the only thing we might change is the stiffness. And if we run it again, it's going to be a whole different ball game of how it's going to behave. And it might not make it in 7,000. It might take more. Or if we change the size distribution, all of these things are going to affect how long it takes to reach equilibrium. So that's why it's really important to be able to have this thing to give you a very good metric that in almost all cases will work, to know that you're in static equilibrium. Because that's what we're going to do. We're going to do this and we're going to say, okay, good. Now we got a pack. Now we're going to go and push it with the top wall and measure things. And that's our oedometer test, right? So, okay, we've gone over time, but I think we're good. I wanted to finish talking about that. And so thank you for your attention. We'll do the exact same thing a week from now, same time, same place. And I hope to all see you then. Okay?
Thank you so much.